Hi, welcome to the Chapter 2 MIPS review for CSE 230, Spring 2023. I am Josh. I'm the code monkey or the code rat. So I tend to handle a lot of the questions and content regarding MIPS stuff. So this whole thing will be around MIPS, how to work with MIPS, the actual coding of MIPS. Yeah. And I am on my Windows boot, so later on I can use Mars. No, IEE is not MIPS for me. I will not be going over the IEEE stuff. I am terrible at the floating point. It is Chapter 3. I believe Andrew is covering that.
That's tomorrow.
That is tomorrow. Make sure you remind him to record as well. So, any questions before we get started here? Before we actually get into the meat of it? No, who's covering Chapter 1? I'm hoping Harsh. If not, Chapter 1's a bunch of equations. Write them down on your note sheet. That's what I would do. Anything regarding performance, just put it on your note sheet. Number 1 recommended tip. Anytime you see an equation, that's like 100% guaranteed note sheet. So yeah, let's see if this actually works. If it's going to hate me. Oh dear. Okay, I just have a blank slide apparently. Who knew? I didn't. Basic stuffs, the stuff that you should know, or the stuff that I think is really fundamental before understanding anything else. If you don't know binary, decimal, and hex, you're in big trouble, big danger. We all know that in base representation, it's a sequence of multiplications or additive multiplications. So binary is nothing more than like 1 times 2 to the power of 0, 0 times 2 to the power of 1 plus 1, on and on. You know that binary converts to decimal, can convert to hex, can convert back to binary. It's all interminglable. Hex is 0 to 9, A to F, for a total of 0 to 15. And converting is pretty easy. For the most part, like decimal to binary is literally just dividing by 2 until you have nothing left to divide. And that's it. Question in chat says, will we have to worry about octal? I didn't see anything on octal octal representation. So I would assume that's not that big of a worry. I'm gonna ignore that. Yeah, that's the basics. If you don't know that, that is the basics. If you don't know that, it was just an example. I ripped off a slide. I didn't actually fact check that. It might become 118. I'm gonna be honest, I don't really care. It was an example to show you the additive multiplications, not the end result. Now, the stuff that I actually care about, which is the MIPS. I actually really love MIPS. I think MIPS is a great academic language. And I think it's a great gateway into things like RISC-V and x86, because it all has the same foundations, if you will. How do I enable that again? I do want to enable that for you guys, but my stuff is really bad. Captions. Yeah, we'll show captions. Save. Turn the transcripts on. As a language, MIPS is pretty easy. It's pretty much mostly documented on the green sheet, and whatever isn't documented on the green sheet is easily found online. There's a bunch of resources on it. So, there's a couple, yeah, like Michael was saying in chat, MIPS is also used for like N64, PS1. So for one of those guys, you might be using it. But for the most part, it's mostly used as an academic language. And there's three kinds of instruction types with MIPS. There's R type, which involves two registers and a destination register. For the most part, RS, RT, RD. The I type, which involves a register, immediate value, and a destination register. And the J type, which is used namely for jump instructions. And by that I mean almost entirely jump instructions. If this makes sense to you as far as how that lays out, and you can read that, most of the MIPS stuff should be pretty easy. The numbers on the bottom just correspond with the bit values or the bit ranges. So bits 0 to 5 are the funked value, 6 to 10 are the shamped value, 11 to 15 are the RD value, RT, RS, opcode, so on. Immediate RT, RS. So if that makes sense, you're good. I don't know why. There. Add and subtract. You've used this 1,000 times. So let's be real. It's add and subtract. Addy is add immediate, and actually sub E does not exist. Sub I, that's not real. And if I can hear you, I need to stop hearing you. Yeah. So the add and subtract stuff is pretty good. We're gonna go through some of this earlier stuff pretty quick, and as we get closer to the back end of it, we'll slow down. Because some of this earlier stuff is really, you've used it a lot. So I'm kind of in the mindset that you should be kind of catching on. Add subtract is just a command. Multiplication division is a little bit weird. In the fact that it stores the results in the low and the high registers, and you can actually just move them from low, move them from high. So MF low, MF high. And division works exactly the same with the low and the high. Where the quotient is in the low and the remainder is in the high. So the weird thing about multiplication division is that they're R-type without having destination register, really. To have a special kind of opcode in the binary, and I'll show you that later. But realistically, I'm thinking you guys have used this a bunch of times. So should be pretty standard on pulling out what you need from multiplication division as far as like the results of that. We have logical operations and immediate or immediate nor. We have a shift left logical and a shift right logical. So you can actually multiply by a factor of 2, divide by a factor of 2, which is actually more like 2 to the power. So SLL1 is a like 2 to the 1, whereas SLL2 is like 2 to the 2. And you're multiplying by that power of 2. That makes sense? Most of you have been using the shift left logical for a lot of your stuff since January, like mid-January, so we're heading into early March. Any questions so far? This is all pretty standard stuff, right? It's just MIPS. Can I go over using and or for things like masks? I don't think that's necessary for your exam. I'm gonna be real with you. When I went over the exam, I didn't have anything like that. So I didn't anticipate using it for masks. How hard is the exam in your opinion? In general, 4 out of 10. 4.5 maybe. General idea. I didn't think it was that bad, and I'm not really good at all the content stuff. I'm just a code monkey. We'll move on to next slide. So big memory. Obviously, we have load word, save word. Again, for load words, the destination, the offset, and the source. For store word, it's the source, the offset, and the destination. This is gonna be really boring until we get to the end. I'll try to make it entertaining. But this is chapter 2 stuff. This is what you learned in chapter 2. Is like this really syntaxy stuff. And this is the part that you probably all want to see. The big dread. Yes, you will have to convert from C to MIPS, MIPS to C, machine code to MIPS, and MIPS to machine code. I saw all 4 of these things on the exam somewhere. So, whether or not you get it, or whether or not it ends up on the final copy of it, or the final draft, another animal. But when I took 230, it was on there. When my friends took 230, it was on there. Last semester it was on there. So it's one of those things where you can assume it's going to be on there. It's like one of those big chapter 2 points. So we'll go over some of it here. And don't worry, if you're not really fast at it, neither am I. I'm actually really slow at the C to MIPS. Well, no. I'm slow at the machine code to MIPS. I'm really slow at that. And the MIPS to machine code, that stuff is really bad for me. So the issue with C to MIPS is that there's not really like a set formula, you know. It's not something that's just like, if you do this, everything will become abundantly clear and everything is fine. Yes, machine code is binary version. Yes. So converting from C to MIPS doesn't really have a set pattern. So what I do when I'm doing it, and this is what I do when I hop into office hours on Tuesday for the first time and I see the homework for the first time, because I definitely haven't had time to look at it beforehand. And I see it, that's what I look at. I read the C code and I actually read it. I break the C code down into segments. I isolate the pieces if I can to like functions, blocks, things that are together. I take the pieces, I decipher the operations, and I slowly unravel them into assembly. And because I've isolated everything, I can build each piece of that code by itself, test it individually, and when I'm done, I can stitch that assembly together. Everyone kind of has their own method for this. Do what works for you, not necessarily what works for me. This is just what I do because my brain likes to break things into chunks. I think that's a good way to do it. As far as like the actual C2 MIPS, I wanted to go over an example of it, but I'm probably going to save all my major examples at the end when I close down my slides and I go over to open up the internet and we go over everything. Couple questions in chat already. Just how complicated do you think the translations are going to get? Probably not that complicated. I mean, you got an hour, 15 minutes. It shouldn't be too crazy. The ones I did weren't wild. Can we go over find immediates for, oh yeah, we'll go over that later. Assembly is literally the step-by-step of all code, including that, including ones that normally have multiple parts. Yeah. There's a lot of it's hard to say what's going to be on the final exam, like the final copy of it. Like I said, I took a draft version of it, but I had like the select all that apply. You should not need to recognize C functions necessarily, not that I'm aware of though. Again, the rendition I ran through was very simple. It was literally just breaking the code down into assembly. So, but also ABS is absolute value, and that's a pretty stock standard C function. You get real familiar with it real quick. So C to MIPS, yeah, there's not a lot to go about that. It's kind of wild, but I think going from C to MIPS is easier than MIPS to C, personally, because going from C to MIPS is just elongating everything to its core components. MIPS to C is like, to me, the Wild West. Again, it's very personal on your own methods, what you want to do, how you approach it. Again, my approach to it, you may find success with it, is to read the MIPS code. I know reading is scary. A lot of students don't do it. I don't do it half the time either. But reading MIPS code is really good. Reading anything's good. So read the code, actually process what it's doing. And then I organize the MIPS code by related labels and look for key logics like indicators like BNE or J. Those will indicate to me something along the lines of maybe there's a function jump here. Like if I see a JAL or a JR, I know that I've entered a function or something, or that allows me to kind of break things apart. And then I walk the MIPS code bit by bit and build a gross big C function. When my first run through of it is really big and nasty, and then I condense it down. Once I have the first copy, you refine it down to what it's actually doing. And at the end, make sure that both are accomplishing the same goal by testing them. That's kind of my approach to MIPS to C conversion. Again, it's going to be a little different based on how you see the code and how you process it, how that code sings to you, or screams at you if it's not singing. But of the two, I think C to MIPS is easier than MIPS to C. For me anyway, some people might find the opposite is true for them. As far as MIPS to machine code, this is like, for me, the slower, annoying side of things. I really don't like it, converting MIPS to machine code. You know, it's kind of really wonky, but it's pretty algorithmic, kind of beautiful in a sense, because you read the instruction, you find the opcode, you check the instruction type, you match each register with its location, the instruction format, then you just fill in the missing information. Voila. You have machine code, except it's a little bit goofier because some of how the green sheet's laid out can be a little strange. I actually have a little section on reading some of the opcode stuff for it. For the most part, it tells you what pieces you need on the green sheet, and it's just kind of slow for me. I'm sure a lot of you might relate. You will be provided a green sheet, so don't worry about that. I don't know about provided extra blank pieces of paper. I think usually the exam has extra blanks stapled to it, but don't quote me on that. This is me saying now. Don't quote me on that because I don't have an answer to that off the top of my head. The machine code to MIPS for me is actually much faster. It's literally find opcode, match, register, fill in detail. And I find that a lot of students who talk to me are actually much faster translating from the binary to the actual MIP because they just break the binary into the chunks and go, what is it? Just be careful with the arithmetic core on the green sheet. Oh, I'm glad you asked. How does the opcode work? Like for add, it goes at the end and zeros at the beginning. Check this out. So for example, you'll see that div has something like 0/-- ////1a, which indicates a 0 in the opcode. So your opcode would just be 0/0/0/0/0, and a 1a in your function section of your R type instruction, which is all the way at the end. So you're going to end up with a 0/1 for the 1 and the 1010 for A. So it actually tells you where it goes. And actually, you'll see that I even have your add example here, where add has a 0/20, where the 0 indicates an opcode 000000, and 20 indicates 10000000. So the slash will indicate where it goes. The core instructions, if there's a slash, it means there's a the opcode and the function. And then yes, you will have pseudo instructions. Can I write that down, what I'm talking about? I have a nice example here. But let me break here and I'll just show you on the green sheet. Behold, the green sheet. Notice how it says opcode function right at the top with a slash. That's telling you that the and then it says hex here. That's telling you that that's how this column is going to be formatted. It's going to be an opcode first, and if there's a slash and another value, yeah, go ahead and point another thing there. I'll drag you over. Boom, right there. I'll actually just take your arrow and move around too. So that right there. So here's your opcode 0. Here's your function code. Opcode 8, opcode 9, opcode 0 with a function code 21. I like this though. This is a good arrow. I can do all kinds of things with it. See, with an R-type instruction, you have an opcode and the function. That makes sense? Kind of see what I'm saying? And if you come on over here, you'll see that we're the arithmetic core instruction set. Opcode, FMT, FT, function. So here you'll see divide is 0 dash 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 1a. It's because it has an opcode, no FMT, no FT, and a function. There's your. That's the long short of it, I guess. And if I were to write it again, it'd just be that again, and then a re-explanation of this again, same thing. Because you're just filling in. Well, you can just look at the green sheet, and it'll tell you. Is it true that R types almost always have 0 for opcode? Well, the green sheet would indicate so. Except some of them are a little bit goofy. But for the most part, yeah, most of them have a 0 opcode. In fact, almost all of them have a 0 opcode. It's just that they have a function code that sets them apart. But all of this is information you can glean from just staring at your green sheet. In fact, you can glean all kinds of funny information from the green sheet. Oh, check this out. How to calculate that branch. Right there. PC plus 4 plus branch address. We'll get to the branching stuff. I have stuff for that later. But here you can even see for like the shift left logical, it's an R type instruction that actually uses the shamped value. So it'd go like right here. So yeah, green sheet's super powerful. It tells you basically everything you need to know as far as like your references. Delete this arrow. I'm gonna shove this arrow off to the side. I might use it later. Slideshow. Again, just read the green sheet and you'll be fine. That's all that's like 80% of MIPS is like logic and green sheet. You can a for loop is a for loop no matter what language you're writing in. An if statement is an if statement no matter what language you're writing in. It's just how do you format the syntax of it. The logic is always there. Any other questions on the conversion from C to MIPS, MIPS to C, MIPS to machine, machine to MIPS before I move on to the next thing? All right, I'll assume not.
I have a question. So, are you going to be discussing about the memory addresses, like with every step of, when you go one step ahead of in MIPS, the memory address changes, and you. It was basically in one of an assignment 5 question 2, like write the MIPS code and then also how the memory address changes every single step.
You add 4 to it every time.
Yeah, and
That's it.
like, oh, that's it.
You literally just add 4 to it.
Because
Because everything's a 32-bit address, right? And there's 8 bits
yeah,
per bytes, and there's 4 bytes, and then you move 4 every time.
okay.
So it's gonna be a 4-step every time. What a lot of people got messed up on was that they forgot that it's in hex code.
Yeah, and I'm guessing in hex code it's like 048C 48C 48C. Is
Basically.
that how it goes?
Yeah, 048C, 048C, 048C. Yeah, basically. Unless you
Okay.
start doing half bytes and stuff like that.
Okay, yeah, that makes sense. And for like, let's say there is an instruction saying jump and link, and so for those sort of instructions, like
We'll
how do
get
we
to
show
that.
them? Okay. Thank you
Not
so
there
much.
yet. You're jumping ahead.
Okay, I'm sorry. Okay, go on. Thanks though. Appreciate it.
Yeah. So pseudo instruction translations, you will probably need this. It's good to know these. I got a little lazy. I'm gonna be honest. I didn't want to type out any actual like registers, so I just called it register 1, register 2 label, register 1, register 2 label, register 1 value, register 1, register 2. These are what they translate it into. They're actually like 2 instructions. Down here, if you can't see it, because I can't see it, because I see my own transcript. It's add R1, 0, R2. And then, yeah, so basically everything's just a combination of shift left, set less than, and then branching if you're equal or not equal. And that's about it. It kind of sums it up. There are more pseudo instructions out there. These are the ones I'm assuming you'll probably have to know. Or at least you might have to know. Like I think there's like something like I have here 6. I think there's like 12 like core pseudo instructions. Some of them just aren't on the green sheet because you don't need to know those for like the intents and purposes of what you're doing. But there's some pretty crazy ones out there. Yeah, this is really just a case of just look at it and take it in. Because ultimately you'll probably end up using the pseudo instruction anyway. At the end of the day, you just might need to know what it translates into. Move is a pseudo instruction. In fact, you'll see it on the left underneath pseudo instruction. And it translates into add R1, 0, R2. Move and move are the same. Last I checked. Unless there is a hidden, a new one that or one I just haven't seen called move, not MV.
Just a small question. Have you posted the slides yet to Canvas?
No, I have not posted the slides. I will post everything together at the end.
Okay, thank you so much.
Anything else about the pseudo instructions? I think this is just a case of memorization on this stuff. You either remember it or you don't. Cool. All right, so this is something that a lot of students struggled with. I have 3 slides here, I think. On functions, addressing, and yeah, fun stuff. So functions, the general idea of a function. If you can remember these 6, 7 steps, congratulations, you can write any function in the world. You can write the recursive functions, you can write the normal functions, you can write literally whatever you want, because, you know, realistically, this is all you need. In fact, this is kind of what C does anyway. So you load up your argument registers with whatever is going into the arguments, be it, you know, 1, 2, 5, 8, 10,000, 43, you know, -12. Doesn't really matter. You're going to jump and link to the function label. You're going to make sure you have enough stack pointer. So give it a little bit more space. Store your return address and whatever else you might need to store in the stack pointer. Do your stuff. At the end of the function, retrieve your return address from the stack pointer. Any arguments you might need. Return the stack pointer to how it was before you entered the function. Usually this manifests in I subtract like 12 at the top and I add 12 at the bottom. If you have any, load up your V0, your V1 if necessary, and then jump return. And that's it. That's the general idea of a function. If you can remember this, congratulations, you can write basically almost everything. How do we use the stack pointer? See my whiteboard? Let me check my... Do y'all see this? Cool. Stack pointer is beyond easy. Y'all know how the stack works, right? Stack go down. Heap go up. Yeah, that's the idea. Adjusting your stack pointer is as easy as saying me want stack pointer go down. You will, I probably hope not. Heap is for not this. Heap is for dynamically allocated stuff. So you will not have to mess with heap. But stack, you'll probably have to mess with stack. So yeah, congratulations. there you go. You've added some space for yourself on the stack. You've given yourself a little bit of stack. If I really wanted to, I could store a word, I don't know, like A0 into 0 SP. Store it like an argument into the stack if I wanted to. And then maybe I'll make sure I store a word, my return address, into my stack. This will actually have to be 4. You actually want to go up, not down. You want to go up in the stack, because you've given yourself, if the stack is like this, right? And the stack pointer was here, and you've given yourself to here. If you go further down, you're gonna be below where you actually gave yourself the stack. So you actually want to go up with your offset. That makes sense? Because what will end up happening in like a recursive case is you'll overwrite things. Because you'll go down again to like here. And if you're using up all that stack that you wanted here, you're going to do it again and you're going to eat that. Whatever you just had, you're going to eat that. So don't do that. Remember, stack go down, store up. And then when you're done, we'll just make a little note here. Do stuff. And it's pretty easy. I'm not going to retrieve my argument. I don't care about that. Let's load word from my source into my destination, which is going to be RA. I stored it at 4 offset. So just reach into wherever I put it. And then it's just going to be, once again, make sure you adjust your stack pointer and give that stack space back. Otherwise, you're going to cause memory issues. That's where leaks happen. When you take stack space but you don't give the stack space back, and you take stack space but you don't give it back. You only have so much stack before you run out. That kind of makes sense? Yes, no, confusion. World's on fire.
I've got a question. Why do we, if we need to alter the stack again, why would we change the number again? So for example, you did the add I instruction to go down 8 in the stack.
Mhm.
So if later on I needed to add, or if I needed to add more to the stack, then why would I just increase the number? I guess is my question.
So here's the thing about why we do this in the function. Can I clear this? Am I allowed to clear this?
Go for it.
Cool. So here's the thing about the stack and why we do what we do with the stack. Stack operates as this first in, first out. Rather, first in, last out. No, I forget the exact term. But basically, wherever we're at is wherever we're going to remove from. So if I'm here on the stack right now, and I move my stack down here, and then I move my stack down here, when I come back, and like if I'm in C, I'm going to come back to this point first, then this point, then whatever point was before. So in order to simulate that would be no different from me saying I need 8 on the stack, 12 on the stack, 8 on the stack. But now I've reached the bottom, so I add 8 to the stack, add 12 to the stack, and add 8 to the stack to get back to 0 on the stack. You have to cycle back through. So we keep diving down because we don't want to ruin what we have in here, or in here, or in here. Otherwise, we'll overwrite things that we were saving, which is why some students ran into issues where their RA, instead of being some number like 808,321, was 241 because they overwrote it because they didn't give themselves a stack or something, and they ended up writing over their stack value. Correct, James. In recursive functions, we store stuff on the stack each recursive call. That is why every time you enter a function, I'm going to stop sharing this screen and go back to this. That is why I say expand that stack pointer, store that return address, and store args if necessary. Because if you are running recursive, it is a bad practice to use ADDI on RA to make it go wherever you want. If you know exactly where you want the RA to go, go for it. The thing is, most of us don't. Having that level of control is usually outside of the hands of the programmer. Set stack pointer to 0. Well, if you set stack pointer to 0, then you're at the top of your stack. If you set the stack pointer to 0, you're at the top of your stack. If you add 0, then you haven't moved your stack pointer, which might be bad. Usually I add at least 4 to store my return address. Kind of gripping this idea better with this function stuff. You need the stack. Stack is critical. I promise you, this is past experience. If you don't use stack when you're doing your recursive, if you're asked to do recursive, or if you're even asked to do a normal function, if you're not using stack, you're gonna get slapped with a negative penalty. You were wondering about the recursive stuff because you were looking at examples online. They just keep subtracting and loading the stack on each recursive call, but not restoring it on each recursive call. I find, yeah, do you mean like adding it, like if I do stack -8, stack +8? It's better conventions to just move your stack back up. Put your stack back where you found it. That's the way I like to think about it, is put your stack back where you found it. It'd be like if you borrowed something from someone's house, and instead of putting it like, putting the plates back, you just threw them on the floor. Kind of disrespectful. Do we ever reassign the stack? I mean, will you ever reassign the stack? That is entirely dependent on where you go as a job. For the most part, in this class, for what you're doing, no. You'll never just reassign the stack. In fact, most people don't want to touch the stack too much like that. That's scary, man. One wrong move on the stack and you get a there's a whole error code for it. It's like a stack crash or something like that. You're not recovering that program. It's just done. Whatever you were running, donezo. So don't crash your stack, and don't crash your heap either. Mainly don't crash your stack. If the stack goes down, that's really bad. That's really bad if the stack goes down. So yeah, that's the general idea. Load up your arguments, jump to your function, set up your stack, make sure you don't lose your return address, do your stuff, make sure you get your return address, put your stack pointer back where you found it, make sure you're returning whatever you have to return, and then return wherever you want to go. Jump return or jump register. That's what it's actually called. I like to say jump return because it's funnier to me, but the correct term is jump register, I think. Cool. So branch addressing. I was asked a bunch about this. There's the technical way, and then there's the how Josh's brain understands it way. It's the current PC counter +4. So wherever you are, whatever address you're at, +4, and then the distance. Or as I understand it, from your next line, the number of lines to get to your location. So, example, I'm on line 13. I have a branch that goes to a label. It goes to like line 25. The immediate value for that is going to be 11. Why? Because 13 plus 1 line, PC +4, plus the distance to get to the next address or to get to your label. That's how I understand it. If you look at her notes and you look at like everything else around that area, it's going to kind of line up with this idea. Just to remember that if your address is further on, if your line is a further line down, you're going to have a positive number. But if you're jumping backwards, you will have a negative immediate value. So you'll jump 1 line ahead, then go backwards in time. That's how I understood the negative one. That the negatives are wacky. But branch addressing is PC relative addressing. I think it's pretty simple once you think of it as in the terms of lines versus like the PC. But once you get into like some pseudo instructions and stuff, I believe that's where the relative, like the PC +4 matters. And the branch distance matters, because remember that pseudo instructions get translated down to 2 instructions. Yeah. Basically, this is just to tell us where we're going with branch instructions. That's all it is. Because, you know, branching is like an I type. No. The branch distance is not a multiple of 4. The 4 times? Y'all are thinking of jumping, bro. We haven't hit jumping. This is branching. You know? No, just like -9. If the label's above the branch statement, it'll be a branch distance is still positive, but you just take 2's complement. No, not really. I mean, realistically, the way I understand it is I go 1 line ahead and I just count the number of lines to get back. Oh, I've moved -10 lines. That's my immediate value. Don't overcomplicate the branch. If you actually look at the solution set, you'll actually see something similar where she quite literally just jumps 1 line ahead and then counts 9 lines down, and her immediate value is 9. Branching is easy. It's a counting game. That's how you determine that. Is the immediate value is just how many of the distance, really. That distance from the next line. Yeah, it's a little weird. PC counts by 4, branch counts by 1. Consider it like the more you think about it, the more your brain twists. So stop thinking about it and think of it the way Josh brain think of it is next line then find how many lines it takes to get to the label. There you go. That's your immediate value. It's not shown in 2's complement as far as I'm aware. It's just -9. I mean, if it asks you for like the binary of -9, it might be in 2's complement. But for the most part, it just asks you for like -9 or like -10. I mean, realistically, you're jumping to a label anyway, so it's PC relative. It's just how far away is it, and then go there. Yeah, branch is pretty simple when you like don't overcomplicate it. Like I'm sure there's a more complicated explanation of it, but like realistically, branching is like go to the next line, then find how many lines. The weird multiplication of 4s and all that comes next. All that weird hoopla, that's jump. Jump is the weird one. Guys ready for jump?
No.
Yeah, it's valid. Well,
I have a question.
I have
So-
probably an answer.
Can you hear me?
Yeah, I can hear you.
Okay. So for instructions like jump in, link to some label, and so how do we convert those lines to hex code?
Repeat that for me.
For lines like JAL, some label, some sort of label, or like jump to some label. So how do we convert those lines to MIPS code? I'm sorry, hex code.
Funny you ask. That's next.
Okay.
That's why I asked if you
Okay.
guys are ready for jump.
Okay. My bad. Go for it. Appreciate
Jump
it.
addressing. It's pseudo direct. It takes the upper 4 bits of the PC plus 4 and takes the 26-bit immediate value, which is just the address of the label divided by 4, and you slap 2 zeros on the bottom and you get a 32-bit address. I'm not kidding. That's how it works. So when you're getting your 26-bit immediate value, which is all you care about, you literally go to the address of it and divide it by 4. So if the address is like 8,000, and it's all in hex, right? So everything's divisible by 4. So if it's like 8,000, you'll just divide 8,000 by 4. And 2,000, that's your immediate value. That's it. And that will take up your 26 bits. The jump, when it's done, will append the PC at the top. The 2 zeros on the bottom, it'll give you a thumbs up. All you have to worry about is finding the address of the label, divided by 4. And if you want to get
Do
the
you mind
address,
just going over through it once again?
yeah. For example, if label is at address 80,000, my immediate value is 20,000. That's it.
Okay. So basically divided by 4.
That is exactly what I said. Yes.
Okay.
Yeah, that's how it works. JAL is the same way. You jump to PC plus 4, 26 intermediate value. Label is just a memory address that you can divide by 4. Slap 2 zeros on the bottom. Done. And all you really care about is the 26-bit immediate value in the middle. So if you see someone asking you, what is the address that you're jumping to, you'll just literally go to the address, find the number, and divide that number by 4. That's it. That's all you have to
To
do.
be honest, I'll be honest, that's the most simplest way someone has told me. Thank you so much for that. Like
I'm trying to give
literally,
myself an example of what I wrote.
this has confused me for so long. Thank you. Appreciate it.
The 2-0, okay, you don't even have to worry as far as you guys are concerned. You don't even really worry about the 4 bits of the PC plus 4 and the 2 zeros on the bottom. Yeah, this is all binary because it's like 4 bits. 4 plus 26 is 30. 30 plus 2 is 32. So yeah, the 2 zeros are binary. The 2 zeros are important for jump, but you know, when you're talking about the immediate value of jump, no. Jump, when it assembles its address, will do it. Yeah. Jump just jumps to a label. Jump and link jumps to a label and stores the PC plus 4 in the return address, and jump register jumps to whatever memory address is stored in a register. JR can hold, I think. I don't know off the top of my head if JR holds the return address divided by 4. Off the top of my head. Because when we look at our jumps, jump register is an R type. It's built different. It doesn't assemble the address the same. Whereas jump does the PC equals jump address, and then jump and link is the PC plus A, PC equals jump address. So we'll move forward and then store that in return address. Yeah. So yeah, jump addressing, it took me a long while to actually wrap my head around it. A long time to wrap my head around jump, like the pseudo direct addressing. And even now, whenever I read new stuff about it, I get confused. So like if I read it and it's explained differently, I get confused again. Like, so what do I actually need here? What am I doing? You know? But yeah, jumps are wacky, dude. I don't even know how they figured that one out or why they built it that way, but that's cool. Yeah, it's literally just the address of the label divided by 4. And the branch is literally just the number of instructions from the instruction after the branch. That's it. I'm sorry, it has probably taken far too long to receive the simplified explanation of it.
This is literally the first time any of us are saying this.
It took me like 3-4 years. Leading zeros. Which leading zeros? What are you
Actually,
referring to?
Can I just post this directly into note resources like right now? Like just to screenshot the slide.
Yeah, probably.
All right, doing that. People need to see it.
I'm gonna be posting the slides anyway. I don't know like which leading zeros. Like, do you mean the 2 zeros on the bottom? Or like the PC plus 4 at the top? Or do you mean like if I have 8,000, do I need the other bazillion zeros before it? Yeah. In binary, it's still 26 bits. So if you have 8,000, it's going to be effectively 22 zeros and 8,000 at the end. At least that's how I see it. It's an immediate value. It's going to take whatever's stored there, multiply it by 4, slap the upper 4 bits of the PC on it, slap 2 zeros on the bottom, say, ah, an address I can actually go to. Excellent. So, still gotta plug it in there. Yeah, no problem. I'm sure someone might have contrary information to me. If someone explains it better, I'd love to hear that. But this is how my brain is understanding it. And believe it or not, but when it comes to the content of this class, I'm like on the same level as you guys. I'm like, some of you are actually better at this than I am. The content stuff is rough for me. Like I said, it took me like 3 years to figure this one out. 3 years to figure out that pseudo direct addressing was literally just dividing the address by 4. Yeah, I'm out of script, which is good because that puts me right where I want to be. This is the part where realistically I'm kind of vibing. I want to write maybe a recursive thing for you, some function stuff. I want to answer whatever questions you have for me about concerns. Oh, and like questions. I'm the code rat, so try to keep the questions within the confines of the vehicle of me being the code rat. Otherwise, you start asking me about floating points and my brain will lock up and I'll sit there like this. And then we'll all look like fools together. And nobody wants that. So if you guys would like, I can write a quick recursive function for you guys. I don't mind. Let me time for you to force you to answer jump addressing's big address works. All right, cool. I'm gonna stop sharing for now. Let me break this down. Let me open up my Mars and I'll swap over to that so that you guys can hopefully see my screen. All right. Y'all see my funny silly Mars?
Let's go.
Yes, we can.
Let's go. All right, cool. Let me make a new file. It's probably gonna be sweet. All right,
I just
so
want to say your background is dope.
the frog.
Yeah, the frog. I love it.
I love the frog. Figure you might as well have fun while they're sitting there monitoring you. But so we have dot data and then dot text. This is how you do it in Mars. This is just an IDE for just assembly for MIPS. I'm not going to stop, kick down, boot over into my Linux boot open my NeoVim. It sounds like a lot of work, and then I have to like put the stream on hold, and this will work.
Just get into 1064 at that point.
Yeah, whatever. So I think it's hashtag for this. It's a pound sign. Let's do a big funny recursive. So let's say let's make a main function. I'll just call it main. This would be kind of where I do everything. I want to go ahead and establish S0 to S2 or S. I'll just do a super basic one of like an addition where I'll just recursively add itself until I reach an n equals 0. So I only need two. Basically, I'll do a multiply function recursively. If that's funny. But so we'll do S0, 0, and we'll do 4. And then in our S1, we'll do like 3. This will be our like this will be like M. This will be N. Objective is to M times N recursively. So that's kind of our goal here. So when I'm thinking about this, I have this little main function. I'm just going to kind of skeleton out my code. I already know I'm going to need like a recursive case to like just iterate through. So I'll just call it recurse. And I'll put a funny up here. This is my recursive case. I'll actually treat my labels exactly like I treat my like a C function with my white space. Because I want to make sure that my recursive case is dramatically separate from the rest of my code. Otherwise, I might mix them up. And that's wouldn't be an issue for like the program, it would be an issue for my readability. Which is a bigger problem. So if we're doing a recursive case, we just kind of want to jump in. But we want to make sure we add in everything into our A's, our argument registers. So let's go ahead and do that. We're going to add into A0 using 0, S1 or S0, and we'll add into A2 or A1, 0, S1. I'll put M into argument register, put N into argument register. Now there's a lot of ways you can do the recursion on this, but has anyone taught you guys the golden rule of recursion? No matter what, you must advance towards the base case. Second rule, always have a base case. Otherwise, you'll infinitely advance and the recursion will go infinitely deep and then you'll crash your program and then, you know, you'll be sad and your computer will definitely be sad. So, always advance towards base case. Always have a base case. So when I start building a recursive function, we'll just go ahead and we'll JAL into recurse. Cool. First things first. For my sanity, let's build a base case. So base case, I want it to be if n is 0, return 0. I'm thinking of it like C, right? If n equals 0, return 0. Something like that, right? I've reached the bottom. There's nothing more to add. I've already added it 3 times. So what do you guys think? How would you want to build it? Like, what's your instinct to check? Or rather, what is the first thing we do? Here's a trick question. First things first. Yeah, James got it. Stack pointer. First things first, we take care of stack pointer. Because it's a recursion, Always take care of your stack pointer. Otherwise, you're going to overwrite something. And then you'll lose points. And no one wants that. So I'm just going to go ahead and add E into my stack pointer. Stack pointer. I only need -4 for this because I'm really only caring to hold on to my return addresses. So let's go ahead and hold on to our return address here. So store word, our return address, we'll just store it at 0 for RA, SP. There we go. And I tried to do a vim command there and make a new line. Let's handle stack pointer first. So now we have the stack pointer. Let's check our base case. And we had a couple options here. We had a branch equal to, branch not equal to. I would say probably a branch equal to would probably work here. What with we want A1 0. What does that work? What would that do? If we're branching for equal to, then that means we have to go somewhere. And that might be an issue. You know? So what's actually correct is going to be that BNE. We want to make sure that if we're not equal to 0, we go to our recursive case. Because in assembly, a lot of things are kind of backwards. That's like one of the goofier parts. And I'll make a new label down here called recursive case. And I'll make a little label here called base case. And you see how I'm building up my skeleton as I go to kind of accommodate my thoughts as the code builds. So we're going to go ahead and go to recursive case here. If our A1 is equal to 0, if our N is equal to 0. If it's not, then we continue with the base case. We're going to set that V0 correct. We're going to add into V0 0 0. You can always just do that too. And then we can do one of two things. You can have either duplicates where you return your stack pointer somewhere else, or you can always just jump to like an exit label, and I'll just make a little exit label down here. And this is where I would do something like, you know, first things first, let's go ahead and load word into our return address 0 stack pointer. And then I'm going to add my stack pointer. I only took 4 out, so I'm going to put 4 back. And then JR RA. This will be my exit. At the end of my recursive case, I'll go here. At the end of my base case, I'll go here. Still tracking, haven't lost too many people. Kind of built a case. We have a base case, a way to get out of the base case. We haven't built the recursive case yet, but we have our main kind of almost there. We have everything kind of set up for that for when we come out. Which means we only have one more thing to build, which is our recursive case. Now, the recursive case, remember, golden rule, always advance towards the base case. So what we're actually going to do is I'm going to subtract, or rather, we're going to build probably some kind of argument together. So if I want to build, if I want to like add together 4 plus whatever comes out of whatever's coming in, then I should probably go get whatever's coming in, which means I need to subtract my n argument and then jump again. So let's do that. So we'll do addy. We are in a1, a1 minus 1, subtract n by 1. We're going to jump and link recurse again. And then we're going to add into our v0 whatever v0 was returned and whatever our big funny number in here is. I'm going to go ahead and kind of close this up. And then we'll just jump exit program, just because I want to get out of here. Exit program. So will this work first try? No idea. Gonna be honest, I'm someone who has to test their code and see what it does. So remember that in order to use this, we have to just save, and then we save, and then yeah, we'll overwrite it. And then let's just try it. Let's see what it does. We'll assemble it. And I wish I could make these bigger, but I can't, but I'll let you know. I'm just going to kind of step through it. So we add our S0, our S1 are good. Our A0 and our A1 are good. And we jump to our recursion. We go ahead, we store the RA. We jump straight to that. Oh, I'm showing you multiplication through addition using recursion. It's a recursion test. It's to show you that it works. People wanted a recursive example. That's why I'm not just using mult. Yeah, it's a simple example of recursion. We go ahead, we subtract our n by 1. Oh, we go to recursion again. Okay, we jump in. Not 0 yet. Bump. We come by. N minus 1. Jump back. Go forward. Same thing. Bump forward. Currently our n is at 1. Our n is now 0. We do not jump now because n is 0. We now hit the add immediates into v0, 0, 0. We jump to our exit. We load word our return address. We add our stack pointer, return address, and then we'll come back here. Now we start watching that v0, which is up here. It's up at the top. It's very small. I'm sorry. I can't make that bigger. I've tried. But now it's 4, add, jump, 8, add, jump. Go ahead, C, add, jump. And now we're back to the exit program. We step, we exit, and our n value is v0 equals 0, 0, 0, 0, 0, 0, 0, 0, C, which is 12, which is 4 times 3. So the code worked on first try. And it wasn't all that crazy. It was just building the code piece by piece. sometimes is really one of the things I noticed with a lot of student code was either they didn't use the stack pointer and it ran fine, because in a lot of assignments they didn't need the stack pointer necessarily to complete it. There are ways around using it. It's just that stack pointer is probably the easiest way to do it, in my opinion. And as far as code getting set up and the return address getting rewritten all the time, sometimes that means that you're grabbing your RA too soon, or you're overwriting into the stack somewhere. If I imagine, yeah. As far as your question, Isaiah, I imagine if she's asking for multiplication algorithm, she wants the algorithm. This is not the multiplication algorithm. This is showing that multiplication can be done with recursion. They're two different concepts. So if she asks for the algorithm, you might want to put the algorithm. As far as like the recursion, stack pointer. Stack pointer is the way to go. You will eventually run out of ways to store your memory. At least conveniently. Yeah, basically. That's how I would do it, because then I'd store it at 0, 4, 8, 12, and 16. Those would be the locations I store. Yeah. So there you go. An example of recursion done live. I don't tend to do well live coding. I tend to fall apart, but that worked out pretty good. Is there anything else like coding wise you wanted to see? Because I foresee coding. There will be a code question, at least one, somewhere. Feel free to just speak up as well. Can you scroll up on the code? Nested function calls, where like you call a function within a function. Isn't recursion just calling a function within a function within a function within a function? That's all you do. Recursion is nested function calls ramped up. Sure, I can do a iterating through a linked list. Can I show that live or nested function calls? What will be valid? How to append on an array. As far as like if you have memory for it, like if you've set aside memory, this is your memory block for your memory. It should be as simple as just like accessing the here, let me file new dot data dot text, and give me 1 second. I will show a quick both of the nested calling, and I can show you the array. Appending on an array is like you still have to worry about how much memory, or like the limits, the size of your array. It's really, do you mean just like how to plug something into a slot in set memory, or like change memory in a slot? Okay, cool. Check this out. Give me 1 second. So if I do dot data and I do dot word, I think it's word, and I do like 4, 5, 6, 9. This is like a 4 size array, and I can actually call it something like tester. like that. So I just like exit program just so you can see what that looks like. If I were to like run new, let me save, and there we go. And run, assemble, just so you can kind of see what that looks like. In memory, when you declare a word like that, the array is already in memory at these locations. So you can actually access this. So what you can actually do is, like here, I would do something like add. Oh God. And then I think I have to do. Trying to remember how to quite get my. We have linked list questions on the test. I have no answer to that. Personally. I will go ahead and I'll build the nested call, and then I'll show you how to putz around with the arrays, because that's a little funny. So check this out. Oh, cool. So I'll come back to the array stuff. Let's do the nested. I'll do main. We'll call it main. We'll do addy into S0, 0, 5, and we'll do like an addy into S4 or S1, 0, 9, 8, and we'll do like an addy into like S2, 0, 10. So this will be like my base setup for it. We're gonna make two functions here. I want a function that's gonna go ahead and do add let's see how I want to do this. No, here, how about this? Better yet, I'll just do two. I'll do one that says add args, and I'll do another function, and I'll just have it mult into what do I want to do it with? Move this over here. And we'll do it, well, we'll call it mult results. There we go. We'll do two. We'll do four like this. Here we go. This is cool. This will work. This will do what I want to do and demonstrate what I want to demonstrate. So let's say I have a bunch of numbers like this in main. We set it up. We get the 8. Now we have like a bunch of numbers here. 2 like that. Like that. Yes, yes. And then we'll go ahead. Let's get to work. First, move into args. So we'll add A3, A2, A1, A0. We'll use all the argument registers. We'll use 0 here, 0 here, 0 here, 0 here. And then we'll put in S0, S1, S2, S3. So first things first, we're going to jump and link into add args. That's where we're going first, right? Next up, we come into the function. This is absolutely recorded. I believe I've said that at the start and in the middle. This is recorded. It is still recording. So first things first, what are we gonna do? What's our we've just got our args, we've jumped into the function. What is the first order of business anytime we jump into a function? Stack. That's right. Let's go ahead. We're gonna add to our stack pointer here. Push that baby out. Realistically, I'm gonna be working with my arguments first. So I'm not worried about storing my arguments. I am worried about my stack, my return address. So I'll only push 4 out for this one. And then I will store word my RA into 0 stack pointer. Cool. Now that we've done that, let's get our addition. So let's say we store into add into T0. What? Yeah, we'll add it into T0 just for now. We'll add A0 and A1 and then add into T1, A2, and A3. Once I have those out of the way and I have them kind of together, next up, we need to set up our next jump into another function. Very simple. No different from any other function jump, right? We're going to set up our arguments. So let's go ahead and set them up. In this case, like I said, I don't care about my arguments anymore. I've done with them what I need to do. They can go away now. If you need to save your arguments for later, you would put them in the stack. I don't need to because I am just going to work with this. So let's do this. Let's go ahead and add into my A0, 0, and T0. And we'll add into A1, 0, T1. This will reset my argument register with a 0 and then add my addition into it. At this point, we're going to jump and link into mult results, which is down here. In here, it should be negative. You are correct. It should be negative. We call that a syntax error or a semantic error, also known as I made a mistake. I've adjusted it. All right, let's go ahead and we jump into mult results. No different from before. Stack. Just in case we're doing more work. By the end of this, it's like I don't care if you're doing like 5 micro things in that function. You add to the stack, you do your thing, you subtract from your stack. That's just how the world's gonna work for you. We'll do another -4. We'll store word, our RA at 0, stack pointer. We will go ahead, we will mult A0, A1. We will store, or rather add, actually I'll MF low into V0 because I only need the bottom. That's all I care about. My item will not be as large as to require the upper 32 bits. Now that I have that set, I'm just gonna load word my RA. Even if it seems redundant, we're gonna do it anyway. And we're gonna go ahead and add our stack pointer. We put it back where we found it. And then we JR RA, which will put us back to here. We have our multiple in V0. That's cool. What we can do now, since V0 doesn't need to change, typically, if you want to be super redundant, you can add into an S register, then back into V0. For sanity's sake, I don't see why we do that. So instead, we're just gonna go ahead and we're going to load word our RA 0 from the stack pointer. Addy stack pointer 4, and then we're just going to JR RA back. In main, this is where I would take things out of that V register because I want, let's say I want it in S4. So we're gonna add into S4 our V0 and 0. No idea if this is gonna work. And then we're going to jump to exit program. This should be a pretty quick run. You'll see I'll blow through the first 3 because we're just adding things into S0, 1, 2, 3. We add into A0, 1, 2, 3. We're going to jump into our add function. First things first, give ourselves stack space, store our return address into the stack. We're going to add our 2 arguments together, put those 2 arguments into A0, A1, which would be a little bit different now because they're going to be different numbers. We can actually double check that they're right by coming down here. We have S0 and S8 is 13 or D. And then we have A and 2, which is 12, which is C. So we're good. We're going to jump and link into mult results. We give ourselves stack space, give ourselves store that return address, do the multiply, move our resulting bit into V0. V0 now has 9C, which we should get by multiplying some big numbers together. Given that we're multiplying 15 and 12 together, we should get something like that. I'll verify that number in a minute. Once we're done here, we give ourselves our return address back, add our stack pointer, jump back with jump register. We're going to retrieve our return address again, put our stack back, jump back, and then you're going to find that we're back here. We're going to store our V0 into S4. 9C is an S4, jump to the end of the program. Done. That's nested. It's no different from any other function, you know? I don't know. I didn't see anything. Like I said, I didn't see anything crazy. I mean, someone might get one on linked list, but like realistically, linked list is just like I have this structure where I have this value, like 2 memory addresses. Yeah, I have 2 memory addresses. One memory address stores a value, one memory address stores another memory address. That's it. That's all it is. When you start making it out to be more than that, that's when it gets confusing. But like it's 2 memory addresses. One memory address holds a value and the other memory address holds a memory address. If you go to the memory address that's held and you access it, it'll have a value. And if you go 4 over, you'll have another memory address. That's all it is. The number one, in my experience, the number one thing that can hurt a student is being afraid of the exam. Yeah, as far as when you get really spicy, you can edit this to have like tester, and then you'd have like dot word, and you'd have like 1, 2, 1, 2, 3, 4, or whatever, and you can get in some really funny array shenanigans. And then the really funny thing, you guys ready for this really funny thing? I'm gonna blow your mind. I don't know if the person who was asking about arrays is still here, but check this out. Array check. Load word S5 tester. Okay. Assemble. Boom. Sweet. We now have that. Like I said, load word becomes Louis. Load upper immediate and all that. Bam. S5 now has the value stored at tester, which means you can use the array as offset. Check this out. I believe this works. I just push 4 over. Yeah, operands of the incorrect. Never mind, I can't do that. It used to be able to, I think, but it's been a while. So you can actually do that, and you actually store the array like address, which is really good. You can also do a LA, which is load address. Which I don't know if that's on the green sheet. Let me double check that. I think load address is on there, but it might not be. Where a lot of some of these other ones, these are some of like those smaller, like side ones for MIPS that you can do. So if you do load address, you just bam, congratulations. S5 now has the address, which means that if I were to say load word into T0, like let's do 8. 8 should give me 3. If I do S5 and you assemble that and you go bam bam, and then you load word, T0 is now 3, which is exactly what I said it would be, because it's just arrays are just offsets. I don't know if load address is usable on the exam, personally. So yeah, hope the live demo coding helped. It's not as scary when you get down to it. It's just code. That's all it is. Numbers on a page. I personally run a twin solid state setup. One solid state has Windows 10 and the other solid state has Pop OS. So yeah, that's all the coding. If you guys have other questions, I technically have 10 more minutes before I hit my 2-hour cap of like how much I have left in me before I go off to finish CSE 240 homework.
Oof.
Yeah, I still haven't finished writing that one. Any other question? If there's no other questions, I'll stop the recording here.